I may ask the next speaker, Mario Trieloff, to the stage here, and Mario will switch to a different topic now and tell us more about something about the solar system. Mario, please.
Okay. Okay, thank you very much. Well, as much of this talk is related to what we know from meteorites about early solar system conditions of planet formation, thermal evolution of the respective meteorite planet bodies and the planetesimals. Some fundamental facts about meteorites first. Well, we know about 40,000 meteorites in the terrestrial collections, and many of them are quite similar to each other, can be grouped into certain classes and grouped according to their mineralogical composition, chemical composition, isotopic composition. What we think today is that these 40,000 meteorites are approximately from about the number of 100 different planet bodies, and those meteorites which could be precisely photographed when they fell, and of which we found actually indeed afterwards meteoritic material, it's only a very small number. Those orbits all were reconstructed to be intersecting the asteroid belt. Now, this is the basic fact that most meteorites indeed are from asteroids, the small bodies between Mars and Jupiter. We also know a few numbers, maybe 100 of Martian meteorites and lunar meteorites, but the substantial fraction is from asteroids. Maybe some are from comets, which we don't yet know. So actually, this is a swarm of random planetesimals that never managed to form a full-sized planet, most likely inhibited by the early presence of Jupiter. Okay, what do meteorites look like? Prominent meteorites are the chondrites. They contribute the most, the largest fraction among meteorites. Carbonaceous chondrites is a group which contains also carbon and water in substantial amounts. And the special thing about them is that they are undifferentiated. They contain pre-accretional structures. For example, the most prominent are the chondrules, millimeter-sized rocky former melt fragments, which formed by some unknown flash-heating event in the early solar nebula. More rare are calcium aluminum-rich inclusions, which are a bit larger and irregular in size. They contain of refractory mineral assemblages, and they were also formed by even higher flash heating or high temperature events in the early solar nebula. All that is embedded in more or less fine-grained matrix, which is mostly micrometer or submicrometer size and rich in volatile elements, which never was subjected to temperatures higher than 900 Kelvin. So we have side-by-side high and low temperature objects, and the meteorite as a whole was never heated to temperatures higher than 900 Kelvin in this case. Now, undifferentiated, this term also refers to the roughly cosmic abundance of iron and nickel. Now, calcium aluminum-rich inclusions are indeed still the oldest objects we know from the early solar system, which were precisely dated. This is not the up-to-date value, but an older value, but okay, it's still valid within uncertainties. And the chondrules, most of the chondrules seem to be 1 to 3 or a few million years younger than CIAs. So what's the difference between meteorites? They contain metal in roughly cosmic proportions, but there are variations within the different groups. Variations concerning the oxidation state of the iron and the total metal abundance or total abundance of iron. Here you have the proportion of the iron in metallic form normalized to silicon and Ci chondrites. Here the iron in silicate and sulfide form normalized to silicon and Ci chondrites. This is a line that corresponds to solar total iron, and you can see that chondritic meteorites roughly have solar proportions of iron, but some are depleted. For example, if you take the ordinary chondrite, which constitutes a major fraction of terrestrial chondrites, they can be grouped. The H group is a high iron content, L group a low total iron content, and the LL group a low total and a low metallic iron content. N-type chondrites have a rather high iron content, but it's completely reduced. It's only in metallic and sulfide form present. Carbonaceous chondrites are generally more oxidized. Okay, in the CAIs, these are prominent objects, and these were the first objects where short-lived nuclides were detected in early solar system matter. This is from Lee et al. 1976, where they analyzed aluminum-rich phases in the CAIs, which are indeed aluminum-rich feldspars. And in these feldspars, they found a pronounced excess of magnesium-26, which is a decay product of the short-lived nuclei aluminum-26. From the slope of this line, one can calculate the initial aluminum-26, aluminum-27 ratio, which is 5 times 10 to the minus 5, and the up-to-date values are not too different from this. And presently, people think that most CAIs originated in a very narrow time interval of maybe 100,000 years or less. Okay, how did short-lived nuclides enter the early solar system? This is an incomplete list of short-lived nuclide of which the presence has been evidenced. Now, among aluminum-26 is also iodine-129, hafnium-182, manganese-53, and others. And most people think today that they were injected into the early solar system by previous nucleosynthesis in mass-rich stars. Just imagine that the solar system as well originated in a massive star cluster. You have side-by-side massive stars which have a quite rapid evolution path, and if they are in their final stages, they emit strong stellar winds and can inject freshly synthesized material in nascent protoplanetary disks of solar masses. And these short-lived nuclides are important in two respects. First, we just can use them for radiometric dating, but with a much better time resolution than long-lived nuclides. And they are important for heating the early planetesimals. Now, just by decay heat, by radioactive decay heat. And the most relevant nuclides in this respect is aluminum-26 and possibly iron-60, because from the mass balance, these are the ones expected to contribute to heat production. Okay, when at this size, if aluminum-26 is present and decays, then the heat can be easily radiated away because of the rather large surface-to-volume ratio. But if the planetesimals are on the order of 1 kilometer or larger, then the heat can be effectively stored. And the reasoning is that if asteroids formed very early, then they had a correspondingly high abundance of aluminum-26, and these experience the strongest heating effects. And in fact, we know differentiated meteorites. These are iron meteorites consisting of an iron-nickel alloy. These are basaltic achondrites, which are devoid of most of their iron. That means they stem from parent bodies which form the metallic core very early in solar system history. And that this process actually occurred fast is evidenced by hafnium tungsten dating, which can date the separation of the metal and the silicate portion of a body. And we also know that the formation of the basaltic achondrites occurred very fast, within a few million years after CAIs. Okay, what are the conditions that are necessary to differentiate a planetesimal? If you want to have a high level of aluminum-26 as a heat source, then two parameters are important: the total radius of the planetesimal and the formation time after CAIs. Now, here you see a region where you can effectively cause partial melting on planetesimals or even differentiation. If a planetesimal is larger than, let us say, 10 kilometers in diameter and forms within 1.5 million years after CAIs, then there will be a high chance that you will have partial melts and differentiation processes on this planetesimal. Now, what is needed for more sophisticated modeling? Well, we need, for example, some knowledge about the starting material. The starting material is certainly material which is highly porous. And for this kind of material, we need, for example, the heat conductivity. Now, the heat conductivity measured in such sample is not very easy, but here in this case it was performed by laser heating, and the heat propagation in the dust sample was monitored by an infrared camera, and so it was possible to model to get the heat conductivity for silica powder with individual powder spheres have sizes in the order of 1 micrometer. And this bridges the gap to chondrites, because chondrites are also slightly porous rocks, but their porosity is not larger than, let us say, 20%, because these are already compactified rocks. Okay, then what you need to do is to solve pressure and temperature stratification in a planetesimal by solving the equations of hydrostatic equilibrium and energy transport. You have to consider that the porosity decreases of this material by hot pressing due to self-gravity. And you also have to consider the different heat sources, not only aluminum-26, but also iron-60, and of course long-lived radioactivities. Now, this is a model. It starts with a highly porous planetesimal and considers subsequent sintering and hot pressing due to self-gravity. Now, here you have the radius of the planetesimal. Here we have the temperature. This is a time-temperature evolution in the center of the planetesimal. This is a time-temperature evolution of the surface of such a planetesimal. And here you see a shrinking of the planetesimal due to the fact of hot pressing due to self-gravity. So this shows the porosity or the volume filling factor. This is the volume filling factor here. We start with a porosity of about 40%, and then the volume filling factor increases in the same way as the planetesimal is shrinking, and these processes are effective. Okay, porosity is particularly important for small bodies. If you have a body of the size 100 kilometer, then you see here for planetesimals is formed 2.5 million years after sea ice for instantaneous accretion. You have a time-temperature curve in the center. And the difference between the solid material and the porous material is significant, but maybe on the order of 100 to 200 Kelvin. But if you have a planetesimal which is as small as 1 kilometer, then the difference is much more significant. For the solid material, you get hardly any heating effects. For the porous material, you can achieve heating up to 1000 Kelvin. So this is, even for small planetesimals, astonishing. Yeah. So, okay, what more is important? It's also the many calculations or models assume instantaneous accretion, but you also can assume that it needs some time to form a planetesimal. For example, here you have different accretion times ranging between 1 and 1.5 million years. And you see that while this is instantaneous accretion, the central temperature will be much higher after a given point of time than in the case of delayed accretion. This is because of course, the level of aluminum-26 is smaller when late accreting material accretes to the forming planetesimals. But it stays hot for a significantly longer time. Okay, not only the duration, total duration of accretion is important, but also the matter of accretion rate. You can calculate linear accretion rates, exponential and asymptotic accretion rates, and you also see that this makes some more or less significant differences in the model. Okay, another important parameter is the abundance of iron-60. Okay, these are calculations for 0% porosity, 50% porosity. What is shown here are temperature profiles, and here you have the radius of the planetesimal. Here you have the formation time of the planetesimals after sea ice. So, for example, here, if you form a planetesimal within, let us say, 1.52 million years after CAI, the temperatures in the center of such planetesimals, if they are larger than 10 kilometers in radius, will be sufficient to achieve partial melting and differentiation. If you form planetesimals 5 million years after CAIs, aluminum-26 is gone or low to a level that you have only about a few hundred Kelvin in the interior of such bodies, no matter of the size. Now, if you add iron 60 at abundance levels which were suggested in the literature, then you will see the effect is iron 60 has a slightly longer half-life than aluminum 26, that you can have prolonged heating effects. That means you have to wait a longer time until you can make large planetesimals which are undifferentiated. If you add porosity, then this is even more severe, but the main effect here is that also smaller planetesimals are affected by strong heating effects. Here, differentiation can occur down to sizes of 1 kilometer or partial melting. Okay, so this is again one of these graphs, and it shows, in my opinion, the most likely condition that we had iron 60 abundance close to 0. This is according to most recent measurements on meteorites. The exact number is the iron 60-56 ratio in the order of 10 to the minus 8, and not 10 to the minus 6 as it was suggested in some studies before. And 50% porosity, okay, this may be too much, but a significant part will be porous. And so the formation timescales will be, here you have the formation of CAIs in this region, larger than a few kilometers, and within 2 million years after CAIs, you will have some differentiation or even core formation effects. Planetesimals, like the carbonaceous chondrite pan bodies, were never heated about temperatures in the order of 700, 800 Kelvin. They must have formed somewhere here, or unless they had been derived from much smaller pan bodies, and they can form here. A question about comets. Okay, they contain some water which was not taken into account in these modelings. But we know from comets that they kept ultra-volatile species like carbon monoxide, carbon dioxide. So the heating effects of comets could not have been strong. But that means you have, if aluminum-26 was distributed homogeneously in the early solar system, then you have to wait a significant time until you can make large comets. All the cometary barren bodies were generally small, but which is certainly not the case for all comets. Okay, then we have a kind of parent body which is in between here. It suffered strong metamorphic effects, but strong heating effects, but they were insufficient to cause segregation of a core. These are the ordinary chondrites. Actually, we know that H6 chondrites, for example, this is a pathologic type. It defines the maximum metamorphic temperature. Were heated on the order of 850 degrees centigrade, while a type H4 chondrite, which should be from the same parent body, was only heated to 650 degrees centigrade. So the effects on the texture are, these are much more coarse-grained by recrystallization processes, and these are much more fine-grained, and you can observe primary relic textures like chondral boundaries, for example. Now the model is that these stem from the same parent body, while the H6 chondrites stem from the hot interior, which cooled very slowly. The type 4 chondrites stem from the outer layers, which stayed cooler, but also cooled more fast. Okay, so this can be quantified in a model like this. We have time temperature curves here. This is for the center of such a parent body, where you have high metamorphic temperatures and slow cooling. This is for the upper layers of such a planetesimal, where you have lower metamorphic maximum temperatures and faster cooling. These numbers are kilometers, the depths of the corresponding material in kilometers of a 100-kilometer asteroid. Now, how can we constrain these cooling curves? This can be done by radiochronometry, by dating meteorites with certain radiochronometric methods. For example, it's important to know in this respect that the age of a meteorite is not just a point of time when the meteorite formed. When a meteorite cools slowly, then we speak of cooling ages. For example, if you date phosphates in which uranium is concentrated by the uranium dead-lead method, then you date the point of time at which the temperature fell below a critical value of 720 Kelvin approximately, which is called the closure temperature. At that temperature, or below that temperature, the diffusion of lead with the surrounding minerals is inhibited. Similarly, for the potassium-argon system, if you date feldspar, potassium-rich feldspar in these chondrites, it has a closure temperature of about 550 Kelvin. This is a blocking temperature when argon-40 cannot diffuse anymore from the feldspar grains. We can do similar principles with fission tracks method from plutonium-244 with different minerals which have different closure temperatures. Okay, and we look at the data. These were already data from 2003. For a number of meteorites with well-defined cooling histories or with a well-defined radiochronometric record, we have evidence that the most strongly heated have the most extended cooling history as defined by radiochronometry. Okay, what can nowadays be done better? For example, we have more data for the individual meteorites. We have new hafnium tungsten data which date metal silicate separation on a small scale for these meteorites. We have uranium lead data for the silicates for pyroxene and olivine. And we have for a few rapidly cooled meteorites aluminum magnesium dates which are not related to chondrule or CIA forming events but to the formation of metamorphic feldspar in this case. Okay, now modeling, of course, also has improved, and the problem is now how to find the optimum model for this data. Now, the optimum model should try to fit the time temperature curves defined by radioisotopic cooling ages by least square fits for a number of well-defined meteorites and their data. You can vary the layering depths for a specific age chondrite and can have a variation of these sets of parameters within reasonable values. So we have a large number of add-on parameters, formation time, the radius of the planetesimal, the initial iron-60 ratio, the surface temperature, which is initially dominated by the surrounding disks, then by solar radiation, the surface porosity, which corresponds to the initial porosity of the material, and the bulk heat conductivity can also be treated as a free parameter. Okay, Henke et al. Used a kind of evolution algorithm to find the best parameters in the multidimensional parameter space, and these are the chi-squares, how they approach with an increasing number of steps or calculations a certain limiting value, and how this covaries with the respective individual parameters. Yeah. So the results of such a fit are, for example, that the formation time of such a planet body is 2 million years after CEIs to provide the appropriate amount of aluminum-26. The iron-60 56 ratio was modeled to be 1.4 10 to the minus 8. And this agrees with recent measurements by Tang and Dofa, who obtained or argued for an iron initial 56 ratio of 1.1. So this would imply, on the other hand, that the heating effect by iron-16 was almost negligible. The surface porosity was substantial, but rather on the order of 20% or 30% than 80%. And all the planetesimals have, in the end, a porous layer outside. Okay, so this is just one example for one meteorite for the radiochronometric data and how the different model curves or for different good fits of these data. Okay, another parameter which was introduced in modeling here was the duration of accretion. And here you see the duration of accretion. And these are the chi-squares of the best model, which was achieved for each preset accretion time. And you see that once you have accretion times which are higher than 1 million years, the chi-square are higher and higher, so it's highly likely that the accretion of this individual parent body did not last more than 1 million years. Okay, now the differentiated bodies. Up to now we had undifferentiated chondritic bodies, now the differentiated. You have to consider melting, differentiation, core formation. That means you have to implement several other things. For example, partial melting of iron nickel or iron sulfide and the silicates, which occurs at different temperatures. You have to consider that heat and melt are transported via advection. You can treat that by a flow in porous media theory or the Darcy flow equation. You have to consider that during transportation of the melt, also the heat sources themselves are redistributed. For example, aluminum 26 is lithophile and rather partitions into a mantle or crust, and iron 60 is siderophile and rather partitions into the core. Okay, so this shows what happens if you take into account these effects or not. This is a central temperature of a planetesimal of a 35-kilometer diameter, formed 1.6 million years after CAIs. This is time, this is the central temperature, and this is a temperature profile over the radius of the planetesimal at the time of maximum metamorphic temperature. Okay, so this would correspond to a curve which essentially doesn't take into account advection and redistribution of heat sources. So this is a typical onion shell model without mass distribution. So this will have a rather large gradient of temperature towards the surface. Okay, if you consider that melt and heat is transported, then you have a model like this. You see that the maximum temperature is not so high, and that the heat is more distributed towards the surface, and the gradient is closer. The more steep gradient is closer to the surface. If you take into account both effects, then you have this curve. And here you see, for example, that the maximum metamorphic temperature is not reached in the center of the planetesimal here, but rather in the silicate layer, where aluminum 26 is concentrated. So this indeed makes some difference. Okay, finally, you can apply several models with conditions in which you get differentiation or get no differentiation and so on. But one important thing is common to all models. For example, here, you have some different cases. This corresponds to the planetesimal surface, this to the center. And these are the fractions of solid iron, solid silicate, and liquid silicate. Now, there are cases, of course, in which you get only partial differentiation, some enrichment of iron towards core. There are other cases in which you get a more or less completely segregated core. Well, this is a snapshot at a time when there's no more segregation of silicate and metal. And at that time, of course, some of the iron is still liquid, some of the silicate is still liquid, but of course that solidifies upon further cooling. Now, but in all cases, you observe a layer on top which did not differentiate, which is partially sintered and partially not sintered. But the not sintered layer is much thinner at the surface. And this means, or opens the possibilities, that some chondrites and achondrite meteorite classes may indeed originate from the same parent body. Okay, so these are summary and conclusions. So we have, for the undifferentiating chondritic bodies, we have for the H-chondrite parent body a best model constrained by radioisotopic cooling ages, which indicate that iron 60 was probably low in this body. We had some significant porosity initially, and that accretion for this body was fast. Okay, still some controversial points, which are more or less used in this modeling, is the role of impact heating. Normally this is neglected, but some groups think there are significant possibilities to cause significant heating effects by impacts. It may be, because we have only for one body, the H-chondrite body, we have a very well-defined data set. For other parent bodies, it's much more difficult, and the data sets are much worse or of less quality. So for these bodies, it may well be that the onion shell structure was not maintained until the end of thermal evolution. We know that meteorites, of course, they experience impacts, but the big question is when did they experience the impacts? Of course, you need some impacts in recent times to deliver small meteorite fragments to Earth. But the question here is if parent bodies like these were disrupted in the initial stage in the first maybe some tens of million years of the thermal evolution or not. There's also one question mark about the distribution of aluminum-26. This was mainly the work by Martin Pizarro's group. We assumed almost homogeneous distribution of aluminum-26. If aluminum-26 was distributed heterogeneously in the early solar system, this will change some of the timescales I've shown here. That, for example, for some matter, it's not necessary to wait a longer time to have undifferentiated bodies. Okay, for the differentiated bodies, okay, so I think, yeah, the metal and silicate segregation process, this is maybe important, can last between 0.4 but also up to 10 million years in such pan bodies. And in most models, an undifferentiated layer remains on top, so yeah, maybe such bodies are the pan bodies of both certain chondrites and achondrite classes. Okay, thank you for your attention.
Yeah, thank you for this nice overview, Mario. So the talk is open to questions. Let's begin on the right-hand side there. Mike.
Hi, John Debus from the Space Telescope Science Institute. A very interesting talk. For the timescales that you're mentioning here, there's still also this gaseous protoplanetary disk that must be present. So does that factor into any of these surface heating conditions that are being modeled?
Yeah, okay. The planetary disk is important for the surface temperature. This will be an important fact, but it's also important in another respect. I mean, if the planetary disk is gone, then you lose all the fine-grained material in general. That means you must have some seeds or precursor material of larger bodies. This at least you must have to, yeah.
Okay, on the left now, Maury.
Yeah, the age of 2 million years that you deduce from these considerations based on temperature seems to me is inconsistent with the ages of the individual chondrules that range up to 4 million years. So yeah. I wonder if these arguments based on temperature and amount of radioactive elements don't miss an energy source, and this energy source could be the gravitational energy released in the formation of the planetesimals. If the model that we heard before is correct, and the planetesimal forms from the gravitational collapse of a self-gravitating clump of chondrules or pebbles, the amount of energy released in the gravitational collapse is huge. And so then you can require fewer radioactive elements to reach these temperatures of 800 kelvins and reconcile the formation time of the planetesimals with the individual chondrule ages. Do you have an opinion?
Okay, it's of course reasonable to consider alternative energy sources, but the limit of 2 million years only refers to, the essential message is that we have to make chondrites after this time, because before you get, if aluminum-26 is homogeneously distributed, only differentiated planetesimals. So that means if you have chondrules that form 3 million years after CAIs, you may wait longer time. Yeah? It's not a basic problem. I mean, for the carbonaceous chondrite parent bodies, 2 million years is also too short. You need to wait for 3 million years or maybe longer to make carbonaceous chondrite parent bodies, so they can accommodate the chondrules that form 3 or 4 million years after CAI. So I think it's not a basic problem.
Okay, in the middle, please, Mike.
So remembering that the building blocks of the growing bodies are a mix of silicate and carbon objects, and the fact that the most large bodies, parent bodies in the inner solar system are carbon poor. And you know, Hans-Peter Gale and Joe Knuth have reminded us of the importance of oxidizing gas phase grain reactions. The question is, are there thermal geochemical processes in, say, kilometer-sized bodies that could alter the carbon to silicon ratio in a bulk way?
Okay, that's a good question. I'm not sure about that. I think we have, for example, the ordinary chondrites. We have some indicators in the minerals, especially in the feldspars, some distributions of halogens, that there were fluids active. But we don't see fluid material left in the ordinary chondrites. So this must have been degassed. And ordinary chondrites is a type of chondrites which we know from the noble gases formed under open system conditions. That means gas that escaped during terminal metamorphism on the parent body that could also escape from the parent body. For ancestite chondrites, that may be different. For carbonaceous chondrites, I'm not sure. Maybe.
Okay, next question to the right.
Andrea Banzatti, ETH Zurich. I have a question as a follow-up on an earlier question by Morbidelli on the formation of chondrules. You invoked shocking heating events, right, in the solar nebula to form this grains. My question is trying to bridge different fields. Is there any evidence, or have you ever thought about the possible role of episodic accretion outbursts happening during the Titari phase, like what we heard about yesterday, FUR outburst, XOR outburst, in the formation of these small grains that need such strong heating events to happen when the disk is still full of gas and dust? Have you ever thought, is there any?
Yeah, there were indeed suggestions that the ordinary chondrite parent bodies form closer to the sun than the carbonaceous chondrite parent bodies. But in general, it's a big problem that we don't know, for many meteorites, we don't know the exact parent body. And even if we would know it, then we would know the exact, we would not know if that parent body resided always in the same place in the asteroid belt or in the early solar system. So I think this problem is unsolved, that we don't know where the individual chondrite classes originated in terms of distance from the sun. I think this is not solved.
But for the chondrules, in terms of strength of the shocking event and in terms of timescales, is there any? There's
only speculations, maybe.
Okay, thanks.
Okay, there's still plenty of time for questions. I see one in the back, but isn't there something from the balcony this time, from the gallery? Okay, you can think about it. In the back first, please.
Hi, this is Gijs Mulders, University of Amsterdam. I was wondering, especially in connection with the previous talk about comets and formation of basically icy planetesimals far out. So we just heard that you can form these things very quickly, but you mentioned also that comets must have formed really late. So what would happen if you form something like a comet really quickly and you take this radioactive heating by short-lived radionuclides into account? Would the comet melt? Would it evaporate? Do you know what would happen in this case?
Okay, my argument was only if aluminum-26 was distributed homogeneously, also in the outer solar system at the same concentrations we have it in the inner solar system, then if you form such a body, a porous body within of 1 or few kilometer size, within the first 4 million years, then the heating effects on comets would certainly be too strong. Now, I'm not sure what that means. Maybe that comet formed a bit later. There may be comet populations in the outer solar system that formed early, but which we don't see as active comets because they already lost their volatiles by intrinsic activity on their parent body. And this should maybe have hydrated silicates on their surface. So,
yeah, Martin Bizarro, Copenhagen. I just want to comment on the previous comment about the ages of the chondrules. There's only 5 chondrules that are dated with an accurate method and a method which is assumption-free. And those ages range from the formation of CIs up to about 3.5 million years. So there's no statistical database. So Mario didn't show those ages for some reason. I don't know why, but you didn't. Okay. To reply to that comment, I think it's a really interesting idea to try to link these transient heating events with accretion processes that are occurring in a disk. And for that, we require a large database of chondrule ages. Now, in our group, we are in the process of dating 50 chondrules. And the expectation is that we'll have some sort of time distribution of these transient heating events, which hopefully we could link to processes which are happening in a disk, such as accretion.
Okay.
So there are no comments from the speaker to this remark, and I don't see any further questions. So let's thank both speakers again, please.